Back first.
Why does you? It's water in a grocery store.
Exactly. There's no way.
Who else said any? Oh.
That's what I've been hearing. It's like, no way.
All right, let's go over this. All right, hold on. Just kidding. Let me put it in attendance really quick. You have like 15 more seconds.
You could put that Tristan is here.
Tristan is absent. Got it. No, here. Here.
Right.
Yes. Okay, now attendance. All right, back to this. So in Rivertown, there are 3 recycling centers, 1, 2, and 3. Each, there are exactly 5 kinds of materials that are recycled: glass, newsprint, plastic, tin, and wood. Each recycling center does either 2 or 3 kinds of materials. There are 3 rules, Jared. The first rule is that any recycling center that recycles wood also recycles newsprint. 2, every kind of material that Center 2 recycles is also recycled at Center 1. And 3, only one of them does plastic, and that one does not do glass. Could A be the answer? Does A violate any of the rules? This is dramatic, yeah. It violates which one? The wood? Any one that does wood has to do newsprint, but look at Center 3.
Yeah, no print.
Does wood, no newsprint, so A can't be the answer.
Right.
Does B violate any of the rules? Which one? I don't know. Does each center do either 2 or 3 things? Yes. Do we have all 5? 1, 2, 3, 4, 5.
Yes, yes.
Yeah. Does each one that does newsprint or does wood, does newsprint as well? Yes. Is every kind of material that center 2 does in center 1? Is there only one that does plastic?
Yeah.
Does that one also not do glass?
Yeah.
Yes. B. B is the answer. I think C violates rule 3 because it does plastic here, but not glass. D violates rule what? Which one does this one violate? Does wood, newsprint, every kind this one does is that one. The one that does plastic does glass, so that also violates rule 3. And then this one, newsprint, plastic, wood, newsprint, plastic, wood. Only one recycles plastic, and here I have plastic twice. So this violates rule 3. All 3 of these are just problems with rule 3. So B is the answer. Yay? Yay. All right, today we will go over probability. We will do 3 things: probability of events, mutually exclusive events, and independent events. First, to find the probability of an event, what you do is you find the sample space of the experiment, which is all the total possible outcomes that could happen. And then you find how many happen for whatever event that you're interested in. And then you'll divide outcomes you're interested in over total number of possibilities. Does that make sense? Yeah, that makes sense, Mr. Lake. Anybody need more time on this slide? Okay, let's try one. So find the sample space for each of these. Find all possible outcomes for each of these. I'm going to do one of these for you. I'm going to do the second option. What are all the possible outcomes that could happen if you toss 2 coins? There are 4 different possible outcomes. The first outcome is they could both be heads. Or the first one could be heads, but the second one is tails. Or the first one could be tails and the second one is heads. Or both of them are tails. So this first thing is just a review of our counting principles. List all the possible outcomes if just 1 coin is tossed, or this one's kind of tricky. 3 coins are tossed. How many different possible outcomes are there? I'll give you not 3 minutes. I'm going to give you 2 minutes. It is 8. There are 8 possible outcomes if you toss 3 coins. And order, if you care about the order. If order doesn't matter, there's even less. If order doesn't matter, there's only 4 outcomes, right? Yeah. Wednesday is holiday sweater day. Thursday is college/sports day. And then Friday is PJ day. I'm seeing this in a email for Spirit Week. What's the weather going to be like on Wednesday? It's 74 degrees. Bring your holiday sweater. Oof. They should switch that with Thursday where it's only 53. Quick audible. Oh yeah, Thursday's college sports day. And you can wear like a jersey or something. All right. Today is this is a lot of Spirit Week, apparently.
Really?
Yeah, I guess.
Since when?
Since now. Candle. Look at you. All right. If I toss 2 coins, what are the possible things that could happen? No, sorry, 1 coin. What did I say? 2 coins? Heads or tails? Okay, very good. Do you want to help me out with the next one? Sure. All right. What if I do 3 coins? Oh, whoa. Okay, okay. That's wild. You did start with heads, tails. Okay, got it. Okay. Perfect. Okay. 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 Add. Okay. Tails. All right, perfect. There you go. Notice, look at your answer, and then look at the board. Now look at your answer. Now look at your neighbor's answer. Look at the board. Did you put squiggly brackets? Yeah. Yes. It is a necessity. Yes. The squiggly brackets means that this is a set of things. This is a group of things that we're talking about. Squiggly brackets. Mason, did you put squiggly brackets?
Yeah.
Mason put squiggly brackets. Okay, now that we know how to find a sample space, we pretty much know how to do any probability. You're just going to find what events you care about, count how many they are, divided by the total number of options. Anybody need more time to write? So, probability of any event E is how many times E could happen over the total sample space. Because your numerator will always be a number equal or smaller than the denominator, your answer will always be between 0 and 1. It will be given to you as a decimal. You can convert that decimal to a percentage. So like this would be a 50% chance, or this is a 100% chance. If the probability is 0, then that event is impossible. If the probability is 1, then the event is certain. There's a 100% chance that it will happen. Note that a key requirement is that each possible event or each possible outcome in the sample space has to be equally likely. Okay. Questions about that? Everybody need more time to write or anything? Okay, let's have you try one. So if I toss 2 coins, what is the probability that both of them will land heads up? And if I have a random deck of 52 cards, what is the probability that I draw from that deck randomly an ace? 3 minutes. Nope, sorry, 2 minutes. Yeah, I forgot to say, this is the last lecture for this semester. This is it. So make sure you cherish every single one of these guided practices.
I'm gonna crowd myself.
That's crazy.
Once you have the answer, really sit and just reflect on your process, how you felt the whole time. Or if you're two people in this classroom, you're assigning. Yes. What's the chances of drawing an ace from a 52 card deck? Four aces in the deck. Oh, out of that, which is what percentage? You should tell. How many? What do you think? What's the chances that top two chords that both of them? That's exactly it. One out of four. 52 in the deck, 4 of them. Tell me that percent. Wait. This should be just 2 points. So instead of 1 out of 8, it's 1 out of 4. The order does matter. For just 2 points? For this one? Yeah. Not 3 points. All right, let's go over this. 2, 6. Nobody. That 6 doesn't. What is the chances of that happening? What's the chances of both of them landing up heads? 1/4. There are 4 options and only one way they can land up both heads, or 0.25 or 25%. Do you want me with the next one too? The next one. What's the chances of drawing an ace? How many aces are in the deck? 4. 4. 4 aces in the deck. Out of 52 possible choices. Now we need a calculator for that one. 4 out of 52 is 0.0769, or in other about is about. So in other words, there's a 7.69% chance. And if I gave you a deck of cards, you grab one randomly, it would be an ace. Yay? Feel okay about these? All right. I know what you're asking, Mr. Lake. This is mild sauce. Where's the heat? I come to this class to do stuff that is, challenging. It makes me question my math abilities, right? I'd have like an existential crisis kind of thing. Where are those? Where are those questions? Here we go. And the Arizona's the pick game. You choose 6 different numbers from 1 to 44. When those 6 numbers match, the 6 numbers drawn when they do the lottery in any order, you just have to have the same 6 numbers. Doesn't matter what order they're in. You win the top prize. What is the probability that you win the top prize if you buy 1 ticket?
100%.
And then if the prize is $1 million, based on your probability, how much would a ticket have to cost to be worth it? Have equivalent value. 3 minutes. That answer will shock you. All right, I'll give you a hint. The first thing you need to find is the sample space. How many different possible numbers are there if order doesn't matter? And then how many of those are winners? I'll give you another hint. If order doesn't matter, then you are doing a combination, not a permutation. How many am I choosing from? And how many am I choosing? Now, why did I do it like that? I don't need to do it like that. I could do it like this. Okay, so again, you're not doing a permutation. The answer is not 44 times 43 times 42 times 41 times 40, and so on and so forth, because the order doesn't matter, right? So choosing 1, 2, 3, 4, 5, 6 is the same as choosing 6, 5, 4, 3, 2, 1. And if you do a permutation, it'll double count those when you don't want to double count. So how many numbers am I choosing from? Well, that's how many I'm choosing. I'm choosing 6 numbers from 44. So I need to do 44C6. If you do that, you get 7,059,052. Out of those possible 7 million or so possible different ways I can pick 6 numbers from 54, how many of those will win? 1. There's only 1 set of numbers chosen from that sample space. If you have that set of numbers, you win. Which is a really low probability. What is that probability? It's 1 in 7 million. It's not easy to turn that to a percentage. There's so many zeros, it's meaningless. A 1 in 7 million chance of winning. So if the prize for the lottery was $1 billion, how much would a ticket have to cost? Well, if you take your chances of winning and you multiply it by what you would win, you get that a ticket would have to cost $0.14. Is that how you do the cent symbol? Right? It's been so long since I've done that. 14 cents. Do you think they sell tickets for 14 cents in Arizona? No, they probably sell them for $5. You're basically, every time you buy a ticket, you lose $4.80. Unless you win. But are you going to win? No. That's true. That's right. That's how they get you. Can't win if you don't play. You won't win if you play, but also you can't win if you don't play. That's how they get you. That's okay. They use that money for public schools, right? I actually don't know what they do with it in Arizona. In Kansas, supposedly it goes to public schools. You think so?
Oh, for sure.
No, I don't know if they could lie about that.
Like for every one person that leaves, they're making like 5 times the amount.
Oh, yeah, that's how they could do it.
We get you.
That's how they get you. Get you. All right, everyone happy? Same thing with a lot, like if you go to a casino and you play the slot machines, it literally says on it that your returned value for $1 is 98 cents. Every time you pull that, you're losing 10% of your money or 2% of your money. Lost another 2%, another 2%. Yeah.
Las Vegas, Vegas, that's the whole thing.
You think it's each machine, at least in state of Kansas, has to have on it the returned value. Yes. Those are, I mean, because they don't care. If every time you pull it, you give them 2% of your money, that is fine with them. They can do that all day. Sure, someone will win a jackpot, but so many more people don't, that they're just handing money around and taking 2% each time.
So sketch. Like,
And though there are some that are lower, there are different machines that have different ones. Like there's some that's like a 93-cent return on every dollar. It's got flashing lights, all that stuff.
you began actually.
Huh?
You began.
I don't. Well, okay, so what I do is when you turn 21, the first time you go to any casino, they will give you free play money to become a member. So they'll give you $25. So I will go put the $25 into a machine, wait for it to whittle down and use up all the free play, then convert it to actual cash at a 96% rate or whatever, and then go take the cash and leave. No, you definitely could win big in Vegas. I think those people end up doing very well with the money too when they win big.
I read somewhere that there's like stuff in the machines. Like if it notices that you're like getting tired of like not getting a jackpot, they'll give you a tiny itty bitty win.
Yes, their algorithms for their return rate are based on an addiction formula, which is how often do they have to give you a hit for you to stay at that machine.
Yeah, and then they got like random people giving you a whole bunch of stuff for free so that you'll stay. They don't.
You get free drinks while you're there, yeah. Free secondhand smoke, as much as you want to breathe.
Yeah. I saw an old lady at Las Vegas when we were doing the fun machine. She was just at it. I was just watching it.
Sure,
Yeah, like pajamas on.
they do. You got to be comfortable while you're playing the slots. All right. What is the probability of mutually exclusive events? These are events where the probability of one and the other. Okay, let me show you. Let me show you how to read. So this is probability of A and B. That's what this symbol is right here. A is a union. It basically means the same thing as the word and does. The probability of A and B happening is the probability of A plus the probability of B minus, or sorry, not and, or, sorry, that's my bad. Get excited. The next one is and. This is or. Is the probability of A or B happening is the probability of A plus the probability of B minus, so this is really important, this is the thing that will mess up. When you two would rub aside and you say, Mr. Lake is saying I'm wrong, why is it saying I'm wrong? It's because you forgot to do this, minus the intersection, which grammatically means the same thing as and. Minus the probability that they both happen. So if I say, what would be a good analogy for this? What's the probability that it either is windy or it rains tomorrow? then that would be the probability of it being windy plus the probability of it being rainy minus the probability that they both happen, right? Because when you told me the probability of it being windy, you've already included in that sample size times when it was windy and rainy, right? When you give me the probability it was being rainy, you included in that sample size the probability that was rainy and windy. So then you have to subtract out the probability that they both happen because you have double counted those options. Does that make sense? If those events are mutually exclusive, then you do not have to do that. Notice the only difference in these formulas is you do not put the subtraction in there. So if I say, what's the probability tomorrow that it's sunny or rainy, right? It's impossible, I don't know. Let's say it's impossible for it to be both sunny and rainy, right? So then you would just give me the probability that's sunny, the probability that's rainy, and then add those two together, because it's impossible for them both to happen. Or another one that might make more sense is, what's the probability that either Kyle or John wins that painting, right?
I didn't put my name in.
It would be the probability that Kyle wins, 0, plus the probability that John wins, right? Because it's impossible for them both to win. There's only one winner. If there was multiple winners, then I would have to find the probability of each and then subtract from that the probability that they both win. Would you like to see an example? Would that help out? Let's look at an example. For example, if you have a standard deck of 52 playing cards, you pick one card at random. What is the probability that the card is either a heart or a face card? So to do this, I want the probability of drawing a heart or a face. What is the probability? To do that, we will do the probability of a heart plus the probability of drawing a face card minus the probability of drawing a heart and a face card. To be honest, you could always use that formula, because if it's mutually exclusive, then what will happen is the probability that they both happen is 0. So you'll just subtract 0. Doesn't really matter if you included it or not. Why did I have my music playing all the time? All right, what's the probability that we draw a heart? Well, there are 13 hearts in the deck, divided by 52. How many face cards are there? It's King, Jack, 10. No, King, Jack, Queen. And there's four sets, so 12. King, Jack, Queen, and hearts, spades, clubs, and diamonds. So 3 times 4, 12. Okay, but how many of those cards are both a heart and a face card? Just 3. King of hearts, Queen of hearts, Jack of hearts. And again, the reason why did I put 12 there? Why did I put 12 there? I'll tell you why, because I didn't. It was a 52. It was just a sneaky 52. All right, the reason again why I have to subtract that 3 out of 52 is because when I counted hearts, I counted the King, Queen, and Jack of hearts. When I counted face cards, I counted again the King, Jack, and Queen of face cards of hearts. So now I'm going to subtract out that because I've double counted it. And then if you add that together, that's what, 22 out of 52? Or a 42.307% chance. All right, do you see how we do that? Why did I made this guided practice so that I just did it for you? What am I doing here? Does this example make sense to you? Do you see And again, if you do, it really doesn't matter if you use the two formulas. You could always just use the first formula and be safe. And then when you ask, what's the chance they both happen? If they're mutually exclusive, that chance will be 0. Anybody need more time on this one? Okay. Next, so here's an example of mutually exclusive. So there's a human resources department that has a compilation of how many employees they have with different amounts of years of service. They want to pick an employee at random from their total. What is the probability that the employee has 9 or fewer years of service? The probability of that of less than 9 years, less than or equal to 9, would be the probability that they have 0 to 4 years of service, plus the probability that they have 5 to 9 years of service, minus the probability that they have 0 to 4 and 5 to 9. Oh, we need the total number of employees, don't we? So how many employees are there with 0 to 4 years of service? 157 out of a total of how many employees? 519. It's in this book. How much is it? 529.
What I miss?
I don't know. He just missed a 10th digit somewhere. Okay, out of 529. How many employees are 5 to 9 years of service? 89. How many employees have both 0 to 4 years of service and between 5 to 9 years of service? None. It's impossible to do both of those things, right? You either have one or the other. They are mutually exclusive. It is impossible to do both. So really, this did not need to be here at all in the formula. It was impossible. All right, add those together, divide, you get a total of 246 out of 529, or 0.465, which is, in other words, a 46.5%. So 46.5% of their employees have 9 or less years of service. Only like half their employees are under a decade. The other half is over, I guess. Yay? Anybody need more time on that one? Okay. All right, so now the next thing we have to talk about is the probability of multiple events. 2 events we will say are independent when the occurrence of one has no effect on the occurrence of the other. So for example, if I roll 2 6-sided dice and I get a 12, that has no effect on what I will roll next. I'm not more or less likely to roll a 12 next, right? They are completely independent. Every single time I roll the dice, the sum that I get is completely random. So we call those independent events. To find the probability of independent events, you find the probability that one event will occur times the probability of another. Yay? Okay. So for example, in Dungeons and Dragons, at 5th level, a fighter gets the ability to make an extra attack. So let's say that your fighter is fighting a troll and needs to roll an 8 or higher to get a hit on a 20-sided dice. What is the probability that both of the fighter's attacks will hit? I just realized this is actually not the best example of an independent event. I know, I guess you rolled a hit, that's fine. But what if the first hit like kills the troll or knocks it prone or whatever? That does affect the second choice. This is real world math that you're doing right now. Well, sure, that'd be weird. You have to like bring a mirror to the table and watch yourself play. Yeah, see, because I took C as a literal, but you meant it metaphorically, which is what humor is. I misinterpreted your statement. Yes.
You take it projects, right?
Yeah.
I think we're gonna do a deep sleep fun.
Are we actually, can we?
I've asked, there's the people that have asked for it before it's done it.
I want to do the painting one.
I can do it. I'm up for another painting.
The painting, my painting was so good.
Favorite projects?
My painting was
You
so
good
good.
Yes? Then yeah, we will probably do another painting one later.
Yes.
You're a friend too?
Wait, second half was gonna be so fun. It's
What are friends too? It gives you your speech credit.
all returners, so I put in
You
there.
gotta talk to yourself. So it gives you your speech credit and your English credit
And you
or
have
fine
four
arts credit.
Yeah.
You count any of those three.
I think Charlie.
And then if you take it again, it can count as.
I know,
one
I'm
of the
so
others.
excited.
Take it
It's
again,
gonna be so
count
fun.
And to think I was gonna drop it for concert.
No,
That would be
so
a
I didn't
mistake.
change it. I didn't change it, don't worry.
Just like, I don't know.
What's your question?
So, I like the class.
What was it?
When was that class? Like, you're gonna go next?
I mean, you have that.
Yeah.
Or, I think it's supposed to. No, okay.
I just made a fan.
He's lightweight.
No.
Sure.
I read like one of my.
Yeah, I'll grade it until
I know.
whenever the last day, is. The 17th?
So fun.
No,
I
I
would so do one.
Oh,
Naturals is.
did you put in a request?
Yeah.
Yes. I did.
Normal.
It'll probably happen after this. but-
See? Hey, hey, she said again that. He said that it wasn't, he said it was fine. Mr. Lake said that on one of the videos. Yeah, you should watch the videos. Oh, I mean, I probably should watch actually then, because I have no idea what it's going on. We really should watch it.
Yeah, you probably, yeah, that's a good idea. Yeah. If you want, there are shorter videos in WebAssign that you can do.
Yeah, but then I don't get to hear your beautiful
Sure.
voice.
I know, that's the con, yeah. All right, let's go over this. That's nobody. Oh, we don't have time. We only have a minute. It's 8 out of 20 times 8 out of 20. Oh, sorry, not 8 out of 20. You roll 8 or higher. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 13 out of 20. Because you roll 8 or higher. So there are 13 choices out of 20 times 13 out of 20. So there's a 42% chance that both of the fighters hit. That was the last one. Oh, we don't really need that. I'll make that bell work tomorrow. All right. That was the last lecture of 2021. That's true. You have some more next semester. Have a good one, everybody.
Okay.